Modeling, Perception, and Learning by Rafael Bogach. I think I'm saying his name right. There's a picture of him here. And there's 5 sections to this paper. We'll just run through. Introduction, simplest example of perception, free energy, scaling up the model of perception, and local plasticity. And so the goal of the paper is basically to build up from, as it says, the simplest example of perception and move up to making a model that is increasingly complex. So it's this idea of predictive coding and making a sort of framework to create a model. So for example, this image here is a sort of version of a model of perception. So the introduction here, there's these ideas of predictive coding by Friston and Rao and Ballard and others. And what Bogach tries to do is build on these to propose some ideas of how it could connect to actual brain and something biological. So as I said before, it starts simple and gets increasingly complex. And in order to fit this idea of something that is biologically plausible, it has to satisfy these 2 constraints, or so Bogach says. And those 2 constraints are, as it says in the paper, local computation. And I'll just read this out. A neuron performs computations only on the basis of the activity of its input neurons and synaptic weights associated with these inputs, rather than information encoded in other parts of the circuit. And we'll talk, maybe go into that a bit more later. And then local plasticity. This is synaptic plasticity, and this is only based on the activity of presynaptic and postsynaptic neurons. And this connects to this idea of Hebbian theory, which I have a little definition of later on, and we'll talk about that then. So the idea is to make a model, a coded model that is of the cerebral cortex, something that could potentially be biologically plausible. So we have this little guy who's going to be our sort of spirit animal for part 2 here. So part 2, this idea of the simplest example of perception. He gives this example of an organism tries to infer the size of a food item based on light intensity from a noisy estimate of light intensity. So this organism that has maybe poor eyesight sees a light intensity and tries to see how big the food is in that direction. And I'm not going to go into any of the formulas he uses for it, but this model that he comes up with uses this normal distribution formula and Bayes' theorem, which other people have talked about as well. And then we want to find the most likely feature value, which we start to incorporate free energy and negative free energy to determine the most likely food size. And in the formulas, it's represented by phi, this Greek symbol. And then possible neural implementation means we're going to start satisfying our 2 constraints, which are local computation and synaptic plasticity. And this means we're going to start using in our formulas some considerations of prediction error, which means each of those little nodes where you have something being connected between these synapses, you're going to have to have, well, sorry, the local computation means it's going to happen right there. And prediction error means how wrong can you be and how likely to be wrong it is, and more or less. So you have synaptic plasticity, and the weight of the synaptic connections becomes something that's important because these connections the weight of these connections become important. And this is part of this Hebbian theory, which I'll get to in the next slide. And local computation is what you do once you've received this information. So yeah, prediction error starts to become a thing. And Here we start getting into the parameters for making a model of learning. So we're going to start using this negative free energy formula to update parameters in our model based on new inputs. And here we get the definition of Hebbian theory from Wikipedia. And sorry, I quoted Wikipedia here, but I just need a quick definition of it. And it seemed like a good one. Hebbian theory is a neuroscientific theory claiming that an increase in synaptic efficacy arises from a presynaptic cell's repeated and persistent stimulation of a postsynaptic cell. And in some ways that I see that is, practicing a phrase over and over again, you're going to make those synapses stronger and more weighted. I hope I'm interpreting that right, but that's the way I picture that. And so it's kind of how do we create a model that imitates that? And then learning the relationship between variables. And this is where we start to look at these connections being weighted. So we have two models here, A and B. This is related back to our critter who's zooming in on us with poor eyesight. So U, this letter U is the light intensity. This phi here is the most likely food size, and 1 is what is determined to be the food size. So from U, which is the light intensity, we go up to this area is where we start to first process this information. And we have our prediction error of the light source, the light intensity, plus the variance in the light source. And this symbol here is telling us that there is a weight to this connection. So, how much this has been reinforced will then control what we determine the most likely food size is. And then this in most likely food size goes on to our error prediction in the past of looking at the most likely food size, plus the variance in past food sizes, and past food sizes go here. So this is all pretty linear. And here is where in B things get a little more interesting. Same connections for the most part, but we have this little function here, H, which is is considered a nonlinear function. So in some of these graphs, I didn't get an image of it, but if you have a graph of what the food size is likely to be, it's going to be very big right where what the food size is, and then kind of drip down, like a very simple bump in a graph. But if you have this nonlinear function connected to it, this graph becomes a lot more wavy and unpredictable. And that's part 2. Moving on to part 3 is where we start to incorporate free energy, and things get much more complicated. And I'll just run through this quickly. And maybe this here is maybe not the most accurate interpretation of free energy, but it is kind of a rough version of it. So posterior probability of a food item size based on the light intensity is going to be this guy here, which is the P of the V and U, with V as a food size and U as a light intensity. P of V of U can have a complex shape depending on, jumping backwards, this H function. And then this new thing can be referred to as Q of V. And dropping those into this Kullback-Leibler divergence, you get to know the free energy here. And if these two numbers are equal, then more or less, then first off, the whole function is 0 due to the way the logarithmic function works. And these last two statements I sort of inferred, I think that's right. Maybe I could be corrected. So if the free energy is 0 here, then the model is a pretty full accurate of the reality there. And the negative free energy is what has been modeled thus far. And the way that maybe this is a wrong interpretation, the way I've been seeing it is this sort of glass half empty, half full, negative free energy and free energy inside of this container. And it depends on what you're calculating on which one you're going to want to look at. Another way I was thinking about it is like say a compressor mixer. You have the initial signal, and you also have the mix of whatever the compressed signal is. That connection is a little more fuzzy and maybe not as direct. Um, but jumping on, so I can not spend too much time on all this, we start to scale up our model of perception. So doing this, uh, we start to increase the dimension of sensory input. So sensory inputs from two or more receptors become modeled as a matrix, a covariance matrix, rather than a single variable. So things start to get extremely more complicated. So instead of having one number as our light source, for example, we have the connections between these two numbers, and they start to, it's always a square because there's a same number in either direction. So we have these receptors that are combining to give a more full image of whatever it is we're perceiving. And then we start to introduce hierarchy of these cortical areas. And this quote is from this paper. It says, sensory cortical areas are organized hierarchically such that areas and lower levels of the hierarchy, such as the primary visual cortex, infer presence of simple features of stimuli like edges, on the basis of which the sensory areas and higher levels of hierarchy infer presence of more and more complex features. So with the this image that we have here of this guy, we take for granted the a lot of assumptions about looking at a screen and putting that all together. Uh, so if looking at this image, you might say some of the lower level areas of the cortex perceive these lines and the connections that these black lines are making, uh, let alone the pixels, and the higher level areas perceive three-dimensional character in some sort of space. So you start to have these different perceptions of what you're sensing. Um, then continuing, we have local plasticity, which is of the last part of creating these our model. We start to learn variance of a single prediction error node. Again, starting small and moving up from single variables to matrices. We have the weight of a connection is modified proportionally to the product of activities of presynaptic and postsynaptic neurons, decreased by constant. Um, this is all just talking about this example that they give where there's a series of trials where a model is learning, and the answer here is essentially about 2, but it starts to the estimated variance. We're learning the variance essentially over 1,000 trials of increments of 0.01. And then we learn our covariance matrix, which is essentially the same thing, but using a matrix, a covariance matrix, instead of a single variable. And this seems like a pretty fitting quote here. There's a stochastic fixed point at the values corresponding to the covariance matrix. Covariance is learned with local plasticity involved in simple Hebbian learning, which is the reinforcing of these synapses, often by repetition. Um, and he kind of reviews what we have going on here. We have he describes this as an extension of Round-Ballard's predictive coding model by incorporating variances that offer new computational capabilities, which here you can weight sensory input by reliability, part of this Hebbian theory. And this use of covariance allows learning of multiple properties, and he uses texture as an example. And multiple hierarchical cortical areas can work together to learn properties of a texture. So you're using multiple hierarchical levels to understand there's a two-dimensional surface, it's kind of bumpy or ridgy, and what do those mean, that sort of thing. And then you can pay more attention to any level of the model by changing synaptic weight, and which he refers to as attentional modulation. Sort of, I'm going to jump back to a model here. You can have these symbols here sort of change in weight so that you're focusing your attention on one synapse or another. And last, I'm just going to make a couple thoughts about some musical applications of this. One basic version is something like a tuner of some sort. Say if it learns it's how to read harmonic series, you can recognize frequencies and determine the note name, synth deviations, something very simple that probably most people have a tuner. Then maybe it can learn chords and temporal relationships, and maybe you could teach it other vertical relationships other than the harmonic series, like something related to, say, Vishnugratsi's quarter tone theories, things like that, other systems. So something could learn something based on spectrum, some pattern recognition. James Tinney's Cohen for String Quartet, which is what we have a stereo spectrogram of in the background of this slide. It's a very simple pattern. You can see it kind of goes up, another one goes up, and you get these very sort of symmetrical lines. And if it were to learn the simple pattern of the piece after a couple repetitions, sort of Hebbian reinforcement of the, I guess the synapses, maybe the piece could continue on and on and on up the spectrum, or maybe go down and down and down, following in that pattern. Any of you guys haven't seen the solo violin version of this piece, here's the score for it. This line goes up, very, very slow glissandi. Then this one goes up to the next open string unison, then up and up and up and up. And ultimately, this process is only limited by the number of strings. Another version that kind of came to mind for me is pattern recognition, such as maybe it can learn the simple patterns in something like Steve Reich's Music for Pieces of Wood and play whatever interprets the version of the fifth part to be. At least, except for when the transitions change, because it's probably hard to learn those, but maybe within each section. So like some of the hierarchical levels of that might be perceive the pitch of one of the wood blocks or claves in that piece. Maybe from that you can catch what the rhythm is, maybe excluding part one, which is just straight eighth notes or quarter notes. Then maybe hear the meter and at what level of subdivision or quantization is happening. And then hear every other incoming voice as a different pitch and rhythm, and then listening to the order of the notes as they come in and approximate what might the next voice do. So it's kind of learning from the patterns of voices 2, 3, 4, 2, 3, 4, and making up a part 5. And then the last version of it is something along the lines of, something like Voyager, George Lewis's improvisation program, and other people have made programs like it. So something along those lines where you use a model, a sort of model of, these sort of cortical responses maybe, and you'd have to do some programming to make this work. So that is a very quick run through of this paper. Hope some of that made sense.